Okay, welcome back. So I think we have learned already a lot on discretizing ODEs to really start to summarize what makes a good ODE solver, right? We have, in the beginning, we have introduced using Taylor series analysis to figure out how accurate an approximation scheme is, right? And then we started learning the forward-Euler. We started learning the midpoint rule, which is a more accurate alternative for discretizing the time derivative. And then we tried to follow what we learned on the Taylor series analysis to derive an even more accurate version of discretization. But we found out that it doesn't work because of stability issues, right? And then we did an analysis using eigenvalues of a matrix to figure out what scheme is stable and what scheme is not stable. And in the last lecture, we actually proved that if I have a stable scheme and the scheme is accurate in discretizing du dt, then the solution we get by applying the scheme would also be very accurate. Okay, by very accurate, what we mean is that if the local truncation error, the error in discretizing the derivative, is of the order delta t to a certain power, then the global error, which means the error in the solution, would also scale with delta t to the same power, right? That's what we mean by it's accurate. But at the end of the last lecture, there is a small twist. That is, although when we apply midpoint rule, which is stable, and although we can show that no matter what equation we solve, the global error converges in second order, right? Scales with delta t squared. But the constant on that O delta t squared may be very large for some equations, while the constant for a forward-Euler can be much smaller for that equation. And we linked that result to a much weaker type of instability, right? The kind of instability when you apply the method, the discretizing method, to a specific equation, not to du dt equal to 0, but to a specific equation, and see and look at the long-term behavior of that result. So it's a different type of stability. We call eigenvalue stability or long-term stability, right? It is not a stability when you look at the fixed time. Rather, it's a stability issue when you look at the infinite time, right? So it's a much more restrictive type of stability, and it's also equation dependent. So to summarize what makes a good ODE solver, first is accuracy in what? In approximating the derivative. That's really the basic ingredient, right? If the approximation error is on the order of delta t to the high power, then we like it. The second is zero stability. Or the stability in solving du dt equal to 0. It's really a very basic requirement. If you don't satisfy these, nothing works. And three is what we started introducing in the last lecture, is long-term stability. We also call it eigenvalue stability for reasons we will see pretty soon. Okay, so this lecture we will dive into the long-term stability. And once we learn the long-term stability, that really completes the list of what makes a good ODE solver. And then we can start looking at, for different equations, how do we choose the best ODE solver. And we'll also learn a variety of different ODE solvers, right? Their respective, all of them are going to be zero stable. and all of them have different levels of accuracy, but they have different long-term stability properties, which makes them suitable for different types of equations. All right, so let's dive into really the long-term stability issue. Okay, so how do we assess